This lecture begins the quantitative examples involving Newton's laws for conceptual physics AB. During my qualitative lectures, I introduced you to Newton's second law, which is the mathematical heart of motion. The equation that describes motion as intuited by Isaac Newton is the following. F equals ma. Now, as I described in my qualitative lectures, on the left-hand side of the expression is the vector sum of the individual forces that are acting upon an object. Okay, and then the right-hand side of the expression is the sum of those forces. In other words, it's some number. This number right here is referred to as the net force. Okay, now the object's acceleration doesn't just depend, however, upon what this number is, that is the net force. It also depends upon the inertial mass of the object itself. The greater the mass of an object, the greater its tendency to remain at a constant velocity. In other words, the harder it is to accelerate, this is referred to as inertial mass. Okay, now in the first of my quantitative examples, we're going to look at a situation where the right-hand side of the expression is equal to 0. In other words, the vector sum of the forces is equal to 0, and then therefore this then means that the object does not accelerate. It has a constant velocity. The specific example that we'll look at is an object at rest. Therefore, on the left-hand side of the expression, the vector sum of the forces, well, if the vector sum of the forces is equal to 0, this then means that all the forces have to cancel out, and they mathematically cancel out in every direction. Okay, so the specific example that we're going to look at, what I'm going to have you do in just a moment is pause this video, and then I want you to take a look at the picture that I've posted for you in today's folder. It's called the lecture demonstration picture. Go ahead and take a look at that picture now. Okay, and then that picture corresponds to the following problems that I have, that I have cast up on my screen. I'm going to take you through the mathematics of that problem, and then towards the end of this video, I'm going to show you that demonstration once again. Okay, specifically the problem reads as follows. A mass of 0.2 kilograms, okay, that's 200 grams, and that's the black laboratory weight that I'm using in the demonstration. A mass of 0.2 kilograms is held by the two strings as shown in the picture. The angles made by the strings with respect to the horizontal direction are 30 and 45 degrees respectively. The values of the tension in the strings are 1.43 newtons and 1.76 newtons respectively. And then what we're supposed to do is show that all of the forces cancel in the x direction. We'll think of that as horizontal. And all of the forces cancel in the y direction. We'll think of that as vertical. We always begin a problem in dynamics by drawing out a force diagram. A force diagram is a vector representation of the forces that are acting upon an object. So for this situation, that vector diagram or that force diagram looks like this. Okay, let me do some erasing here. Okay, there are three forces acting on the object, and the object itself, by the way, has a mass of 0.2 kilograms, that is 200 grams. More times than not, we always work in metric SI units, so we write the mass in terms of kilograms. Okay, now there are three forces acting upon the object. First of all is the weight mg, like so, straight downwards. And then we have the first tension from the first string called T1. This right here is the value of 1.43 newtons. Okay, and then if this right here is the horizontal direction, this angle right here is given to us. This angle here we're going to call theta. That's equal to 30 degrees. Okay, and then we have the other tension vector. We'll say that's pulling like so to the upper left-hand side. We're going to call this one T2. This is numerically given to us as 1.76 newtons, like so. And then right here is the horizontal direction again. With respect to the horizontal direction, this angle here is given to us as 45 degrees. We're going to call that angle phi, like so. Okay, now we're going to think of components here in the x direction horizontally and vertically as well. And what we're supposed to do, first of all, is show that the x components cancel out. So then therefore, here's then how we write F equals ma for that situation. The sum of the forces in the horizontal direction is equal to 0. This symbol right here mathematically means sum. So the sum of the forces in the x direction, that is horizontally, has to equal 0 because there's no acceleration horizontally. If this right-hand side of the expression was something other than 0, this would then mean that the object is accelerating horizontally. It's not doing so in this case. Okay, now how do I find the forces in the x direction? Well, what I have to do is I have to take the tension vectors here, T1 and T2, and resolve them or break them into components. To some extent, I've already been doing so here on my diagram. For example, right here in the x direction is this component of T1 that points horizontally, and then right here is the component of T1 that points vertically. Okay, do the same thing here on the left-hand side for T2. Right here is the component of T2 that points horizontally, and then right here is the component that points vertically. Okay, now I'm going to have to use a little bit of basic right triangle trigonometry here in order to find the components of T1 and T2 in the x direction. Let's take a look at T1 first. Okay, so for T1, let's take a look at cosine. If you remember the basics of SOHCAHTOA, recall that cosine is adjacent over hypotenuse. So on the right-hand side here, the cosine of the angle theta is equal to the adjacent side right here. We're going to give this a name. We're going to call this T sub 1 sub x, and then divided by the hypotenuse, which is equal to T1. So adjacent divided by hypotenuse. And now let's go ahead and move the T1 here to the left-hand side to get the x component by itself. Like so, and now let's go ahead and calculate that number numerically. All right, so in my calculator, I now take the value of T1, which was 1.43, and I multiply that by the cosine of 30 degrees. I'm in degree mode in my calculator when I do this, and rounding it off a little bit, it's about 1.24 newtons, like so. Okay, and now this guy here, the adjacent component of T2 that points in the horizontal direction, we're going to call this T2 sub x. It should exactly cancel out with this, minus a little bit of round-off error. So let's see if it does. Once again, I'm going to use a little bit of basic trig. I'm going to use here cosine. So cosine of the angle phi is equal to the adjacent side here, T2 sub x, divided then by the hypotenuse here, T2. Cross multiply the T2 here to the other side to get T2 sub x by itself, like so. So now what I calculate here is the value of T2, which was 1.76 newtons, multiply that by the cosine of 45 degrees. And this then comes out to be about the same thing, 1.24 newtons. So this 1.24 newtons in this direction exactly cancels out with this 1.24 newtons in this direction as well. Here's then how we write F equals ma for this situation. We have T1 sub x minus then, because it points in the opposite direction, T2 sub x is equal to 0. And as we saw here with the mathematics, this x component and this x component cancel each other out. Okay, now the same thing should happen vertically as well. Let me do a little bit of erasing here to illustrate. Okay, so now the sum of the forces, there we go. The sum of the forces vertically, that is in the y direction, has to add up to 0 as well, because once again, there's no acceleration in the vertical direction. So everything has to cancel out vertically. Okay, now vertically, this component here of T1 pointing upwards, this component here of T2 pointing upwards, these two guys here added together have to cancel out with the weight mg downwards. So let's see if they do. So I'm going to call this component here of T1, T1 sub y. Let me write this correctly. Like so. I'm going to call this component here of T2, we're going to call this T2 sub y. And then once again, we're going to use a little bit of SOHCAHTOA to calculate those components. In this case, specifically sine. So let's take a look at the angle theta. So the sine of the angle theta is equal to the opposite side here, T1 sub y, divided by, right here, the hypotenuse, T1. So let's go ahead and move the T1 here to the other side to get the y component here all by itself. Like so. And now here's then what I punch into my calculator. 1.43 times the sine of 30 degrees. So 1.43 times the sine, there we go, of 30 degrees. And that comes out to be about 0.72 newtons, like that. Okay, let's do the same thing over here for T2 sub y. We're going to use the sine of the angle phi. So the sine of the angle phi is equal to the opposite side here, T2 sub y, divided here by the hypotenuse T2. Once again, this is using sine from SOHCAHTOA. Okay, now we'll take the T2 and move it here to the other side. Like so. And now I'm going to punch in the following on my calculator. So 1.76 newtons for T2 times the sine of 45 degrees. Okay, and this comes out to be about 1.24 newtons. But then don't forget we also have the weight mg downwards. Let's see what the weight is by taking the mass, 0.2, and then multiplying it by 9.8 meters per second squared. Okay, so 0.2 times 9.8, and that value comes out to be 1.96 newtons. And then here is then how we specifically write F equals ma for this situation. We have right here this positive 0.72 newtons, plus then this positive right here, 1.24 newtons, but then minus, because it's pointing downwards, the weight mg of 1.96 newtons. These guys here, minus a little bit of round off error, should add up to 0. Well, take a look at the math right here. 0.72 plus 1.24. So 0.72 plus 1.24, sure enough, that's 1.96, which cancels out with this 1.96, and then therefore the sum of the forces is equal to 0. So if an object is at rest, it has an acceleration of 0, it's at a constant velocity of 0, this then means that the forces acting upon it all have to cancel each other out. That's what we've shown here in this example. Okay, to conclude this portion of the lecture, what I'm going to do is I'm going to move my phone because I actually have this set up as a demonstration, again, over here on the table that's behind the phone. So let me go ahead and briefly move my camera. Like so. Okay, and then take a look at the demonstration once again. Here it is. And then I have the string on the right-hand side. That right there is at the 30-degree angle. The one on the left-hand side is at the 45-degree angle. And then the black laboratory weight right there just above the table, that has a mass of 0.2 kilograms. Okay, and then right here is a spring scale attached to the string, so it reads the tension. And then take a look at the right-hand side on the spring scale, which is in terms of newtons. Notice the value of the force there is a little bit less than 1.5 newtons. That's the 1.43 newtons that we used in the example. Okay, and then right here is the spring scale attached to the second string. This right here is giving us the value of T2, also in terms of newtons. And then in the problem, the value of T2 is about 1.76 newtons. Here, it looks to be about the same on the spring scale, like so. So if the object has an acceleration of 0, as it does in this example, this then means that all of the forces cancel out, and they cancel out in every possible direction. Okay, let me go ahead and conclude this video here.